Above the South Atlantic Ocean, stretching from Chile to Zimbabwe, lies a region that has earned an ominous nickname, the Bermuda Triangle of Space. Officially known as the South Atlantic Anomaly, or SAA, this bizarre dead zone keeps frying satellites and posing unprecedented challenges to humanity's orbital infrastructure. As Earth's magnetic field continues to weaken and shift, understanding this phenomenon has become critical not only for space agencies, but for every person on Earth who depends on satellite technology for communication, navigation, weather forecasting, and global financial systems. The South Atlantic Anomaly represents one of the most significant threats to our modern technological civilization. When satellites pass through this region, they encounter intense radiation that can knock out onboard computers, corrupt data collection, and cause permanent damage to sensitive electronic components. The anomaly has expanded by an area nearly half the size of continental Europe since 2014, while its magnetic intensity continues to weaken. This growth pattern suggests that the problem is accelerating, raising urgent questions about the future reliability of space-based infrastructure. Understanding the invisible threat. To comprehend why the South Atlantic Anomaly poses such a danger, we must first understand Earth's natural defense system. Our planet is surrounded by the Van Allen radiation belts, zones of trapped particle radiation predominantly consisting of protons and electrons. These belts normally protect us from harmful solar wind and cosmic rays by deflecting charged particles away from Earth's surface. However, in the region above the South Atlantic, Earth's magnetic field exhibits an unusual weakness, creating what NASA researchers describe as a slowly splitting dent in our planetary shield. This magnetic weakness allows high-energy particles from the Van Allen belts to dip much closer to Earth's surface than normal. Satellites orbiting at several hundred kilometers altitude pass directly through this intensified radiation zone, exposing their delicate electronics to bombardment by energetic protons and electrons. The effects are immediate and often catastrophic. Particle radiation in the SAA can disable computer systems, interfere with scientific instruments, and cause what engineers call single-event upsets, where individual bits of memory flip unexpectedly. The Hubble Space Telescope provides a stark example of how the SAA affects operations. Astronomers must carefully schedule observations to avoid passing through the anomaly, as the radiation creates noise in images and can damage sensitive detectors. Similarly, the International Space Station experiences increased radiation exposure when traversing this region, requiring additional shielding and operational precautions to protect both equipment and crew members. Concrete case studies. Real-world impact. The theoretical dangers of the South Atlantic Anomaly translate into very real operational challenges. In 2020, multiple commercial satellites reported unexplained glitches and temporary system failures that investigators traced back to SAA passages. One telecommunications satellite serving South America experienced a complete communications blackout lasting 47 minutes after encountering an unexpected radiation spike during an unusually active solar period. The European Space Agency's SWARM mission, designed to study Earth's magnetic field, has provided crucial data documenting the anomaly's expansion. Since 2014, satellite measurements have confirmed that the SAA has grown by approximately 2 million square kilometers, an area comparable to half of continental Europe. More concerning still, the data reveals that the anomaly is not just growing, but also splitting into two distinct lobes, suggesting complex changes in Earth's core dynamics. NASA's ICON mission has tracked these developments with precision, revealing that the western lobe of the anomaly has strengthened, while a new secondary lobe has emerged off the coast of Africa. This bifurcation indicates that the underlying geophysical processes driving the anomaly are evolving in ways scientists do not fully understand. The implications extend beyond academic interest, as each lobe represents a separate hazard zone that satellites must navigate. Commercial satellite operators have adapted by implementing redundant systems and developing sophisticated radiation-hardened components. However, these solutions come at significant cost. Radiation-hardened electronics can be 10 to 20 times more expensive than standard components, and the additional shielding required adds weight that reduces payload capacity or requires more powerful launch vehicles. For smaller satellite operators and emerging space nations, these costs create substantial barriers to entry. Expert perspectives on the growing crisis. Dr. Jürgen Matzke, a geomagnetism expert, emphasizes the urgency of understanding the SAA's evolution. We are witnessing fundamental changes in Earth's magnetic field that have not occurred in recorded history, he notes. The rate of change in the South Atlantic Anomaly exceeds our predictive models, which means we cannot accurately forecast how it will develop over the next decade. Space weather specialists point out that the SAA's effects compound during periods of heightened solar activity. During solar maximum, when the sun produces more frequent and intense solar flares and coronal mass ejections, the radiation environment in low Earth orbit becomes significantly more hostile. Satellites passing through the SAA during these periods face exponentially higher risks of damage. The combination of the South Atlantic Anomaly and extreme space weather events creates a perfect storm for satellite failures, explains Dr. Andrew Hands, who has studied radiation effects on spacecraft. We need to develop better predictive models and more resilient satellite designs if we want to maintain reliable space-based services. Industry experts warn that the growing anomaly threatens not just individual satellites, but entire constellations. Modern communication networks rely on hundreds or thousands of small satellites working in coordination. If a significant percentage of these satellites experience degradation or failure due to SAA exposure, the entire network's performance could suffer, affecting millions of users worldwide. Impact analysis. Economic and societal consequences. The economic implications of the South Atlantic Anomaly extend far beyond the space industry. Global positioning systems, which underpin everything from smartphone navigation to precision agriculture and autonomous vehicles, depend on satellites that regularly traverse the SAA. Any degradation in GPS accuracy or availability could disrupt supply chains, transportation networks, and emergency response systems. Financial markets rely on precise timing signals from satellites for high-frequency trading and transaction verification. Even microsecond disruptions caused by radiation-induced clock errors could trigger cascading failures in automated trading systems, potentially causing market instability. Insurance companies now factor SAA-related risks into their satellite coverage policies, with premiums increasing for orbits that pass frequently through the anomaly. The scientific community faces particular challenges. Space telescopes and Earth observation satellites must either avoid the SAA entirely, reducing their operational efficiency, or accept degraded data quality during passages through the region. Climate monitoring missions, which require consistent long-term data collection, struggle with gaps and inconsistencies introduced by radiation effects. For developing nations, especially those in South America and Africa located beneath the anomaly, the consequences are particularly acute. These regions already face challenges accessing reliable satellite services, and the intensifying radiation environment threatens to widen the digital divide. Satellite internet providers must invest heavily in redundancy and error correction to maintain service quality over affected areas. Looking forward, mitigation strategies and future challenges. Addressing the South Atlantic Anomaly requires a multifaceted approach, combining improved prediction, enhanced engineering, and strategic planning. Scientists are deploying new satellite missions specifically designed to monitor the anomaly's evolution in real time, providing data that will improve predictive models and help operators anticipate hazardous conditions. Engineers are developing next-generation radiation-hardened components that offer better protection without excessive weight or cost penalties. Advanced materials science research focuses on creating semiconductors and memory systems inherently resistant to radiation-induced errors. Machine learning algorithms now help predict when satellites are likely to experience SAA-related issues, allowing operators to temporarily shut down non-essential systems during high-risk passages. However, these technical solutions address symptoms rather than causes. The fundamental driver of the South Atlantic Anomaly appears to be changes in Earth's outer core, where molten iron flows generate our planet's magnetic field. Recent research suggests that a mysterious force within the outer core may be responsible for the anomaly's growth and the weakening of Earth's overall magnetic field. Understanding these deep Earth processes requires interdisciplinary collaboration between geophysicists, space scientists, and climate researchers. Some experts propose more radical solutions, including deploying protective magnetic shields in space or establishing alternative satellite architectures that minimize exposure to the anomaly. Others argue that humanity must prepare for a future where certain orbital regions become effectively unusable, requiring fundamental redesigns of space infrastructure. Conclusion: a warning from above the South Atlantic Anomaly serves as a humbling reminder of our dependence on natural systems we barely understand. What began as an obscure geophysical curiosity has evolved into a pressing technological challenge with far reaching implications. As the anomaly continues to grow and split, it forces us to confront uncomfortable truths about the fragility of our space based civilization. The stakes extend beyond satellite operators and space agencies. Every person who uses GPS navigation, checks weather forecasts, streams video content, or conducts online banking relies on infrastructure vulnerable to this invisible threat. The Bermuda Triangle of Space is not a distant abstract concern, but a present reality affecting daily life across the globe. Addressing this challenge requires sustained investment in research, international cooperation, and public awareness. We must support the scientists tracking the anomaly's evolution, the engineers developing more resilient technologies, and the policymakers ensuring equitable access to space-based services despite growing hazards. The truth about the Bermuda Triangle of Space is that it reveals both the remarkable achievements of human ingenuity and the profound vulnerabilities of our technological society. How we respond to this challenge will shape the future of space exploration and the reliability of the systems upon which modern life depends.